How's it going, everybody? So I'm going to do a 7-part series on differential equations. The last series was a 5-part series I called the initial conditions. But we're gonna really focus on philosophically what it means to try to solve physical reality. Okay, and we have classical and quasi-explicit methods of solving differential equations, and the goal of this video is just to track, the rise and fall of the specific solution, hubris, if you will, of the 19th century, which was this mere mathematical optimism that we could essentially describe physical reality in terms of explicit formulas, which were finite combinations of elementary functions and integrals, so we could write the equation down and you'd be able to solve it exactly, right? In this notebook, we're going to explore that the exact methods that we use to solve differential equations have some really clever tricks up our sleeves and geometric insights to reduce the differential equations to simple integration. But as we push these methods to their limit, we're going to watch them break, and we'll see that the emergence of chaos and the failure of standard calculus, and also the need for something called renormalization to tame infinities and sweep infinities under the rug. Essentially, we're going to need these ways. We're going to need these methods to solve the differential equation themselves, or find something that actually satisfies those equations. So, let's first start with really defining what a differential equation is, and the geometry of quadrature. So, most ODEs, or ordinary differential equations, these are first order, and we can reduce them to just quadrature, some area, and that means that we can just solve them with integrals. We can integrate along a curve or whatever, right? Integrate along a field, and essentially, we want to separate the variables, and in terms of m and n, and then just integrate them, right? And what one can find is that if the condition that the partial derivative of this function here that you're integrating with respect to x, if you integrate, or if you take the derivative of that with respect to y, and then it equals to the derivative of this function here with respect to x, and if that equals each other, then the vector field is what we'll call conservative. And what a conservative field looks like is this. Okay, we have essentially the existence of a potential function such that m is equal to the derivative of that potential function, x, with respect to x, and n is equal to the derivative of that potential function with respect to y. All right? And what that means is that solving the ODE is just finding the level sets or the contours of this potential surface. Okay, so if you know the potential surface, you can know all the arrows to draw out of it, or the set of all the solutions or curves that we could possibly have, and just drag or drag some path on that surface and follow the arrows. That's the solution. Okay, and so it's really important to see that a solution is just a matter of walking along the contour lines of that surface. But if we switch then to this idea of an inexact field, or a non-exact rotational vector field, what does that mean? Well, you can't simply just integrate this. All right. So in the classical arsenal, we need to fix this by multiplying the equation by something called an integrating factor. All right. So what the integrating factor does is it's going to rotate our coordinates, okay, by some mu of x. All right, or mu of y, whatever. You're effectively going to warp the space that you're integrating with respect to. We're going to warp the space such that you can integrate it, and stretch the coordinate system until the curl will disappear, and then the system becomes solvable again. But what if the equation is nonlinear? So we can look at the Bernoulli equation where we have some y to the n, right? And this is a specific nonlinear form that allows you to linearize it. And the substitution u is equal to 1 minus n. This reveals that nonlinearity is actually kind of an artifact of coordinate choice. Okay, and often linearity is just is a matter of perspective, because if you take the Riccati equation, which is a special case for n is equal to 2, you can discover a miraculous substitution. By defining y as the logarithmic derivative of some new variable u, we can transform this difficult nonlinear problem into a linear one. And we can take a look at what this equation actually does here. As you can see, the nonlinear solution y kind of shoots up to infinity and blows up in finite time. And this kind of looks like it's catastrophe, right? Because it's just that doesn't, and you can move it around as well and get different artifacts of your perspective. You can get 2 of them, right? Because there's a u squared at the bottom. Well, it turns out that the underlying linear solution actually just crosses 0 here, all right, or it approaches 0 itself here. And that's really what's happening, right? We're getting division by 0 in this nonlinear world, but in the linear world, it's fine. It's perfectly, there's the singularity is just an artifact of the coordinate we chose and not the physics itself, okay? So that's important to realize, but these tricks, again, have a limit, okay? And let's really see this in action. So what we can do here is basically deny the illusion of the 19th century, which is that every system could be solved if we were just clever enough. That dream dies, and you can really see this instantiated from Lorentz, who discovered this thing called the attractor, and he was actually a weather scientist at MIT, or climate scientist or something like that. And this was originally for equations that were being used to model atmospheric science, okay, or the weather. And so we have a deterministic system here of 3 variables, okay? And at low energy, we see that this system here can, if we follow the trajectory of this path at low energy, it's just going to go to a stable fixed point. You see that? So, again, if I increase the energy, the Rayleigh coefficient, it's like bending a little bit and doing stuff, or in this case, it's kind of doing this weird thing, but then going to that stable fixed point, right? Because there's other factors that are influencing the trajectory or pulling on that trajectory. But essentially it's going to a fixed point. That's what you need to understand, okay? But if we increase it to, let's say, 27, what happens is we get this, okay? And this is kind of a mess. One single trajectory is never gonna come back to the same spot again. And this isn't a stable solution. We don't get a formula. We actually get a fractal solution to this differential equation, because the trajectory again is never going to repeat, and it stays in a bounded region. So because the system is sensitive to initial conditions, there's no closed form solution to this series of this basic system of 3 differential equations. We cannot write a formula for this, and the exact methods have officially failed us at this point, okay? So when elementary functions like sine and cosine and stuff fail, then what do? Well, we need to invent new ones called special functions. And these are functions that are very important to physics. The Bessel functions allow us to describe basically, but they're essentially transcendental ordinary differential equations that we define in terms of some choices for A, B, and C. And the ancestor of all these functions here is the hypergeometric master function, okay, master equation. And this is a ordinary differential equation with some chosen, A, B, and C. And essentially they become confluent limits because there's particular singularities that you can do and solve the differential equations by means of series solutions. And you would factor out these singularity points to get polynomial solutions in the complex plane. Okay, that's what the z argument is for. And this allows us to get information out of. We discussed holomorphic functions in our last series, But what's really important about this is we need ways to describe membranes that are vibrating, right? Two-dimensional, you know, systems where if I bang on it, the membrane itself is going to vibrate and give us, things that are not sine waves or cosine waves, but they solve these equations here, okay? Or if I, in terms of, like, if I have a source, an electromagnetic source, and it's vibrating, it's emitting waves in 3 dimensions, I need Legendre polynomials. Or if, I have a quantum system, that I solve the Schrodinger equation or whatever, I need some polynomials to use to describe that in this quantum harmonic oscillator, okay? So, this is all encoded within the hypergeometric master equation. Okay, so that's just something to be to understand. But these functions have really complex personalities, because if we look at something called the area function, which is whenever all the poles line up together at a singular point, and looking at the particular differential equation that comes from that's from all the zoo of differential equations, the area function is very special because well, let's first look at it in the complex plane first. So here's the real part, here's the imaginary part of the area function, and here's its magnitude, or here's the logarithm of the magnitude of its argument, okay? As you can see, really, this height is going to represent the magnitude of the function, and it's pretty polite. But if you notice these red lines, these red lines are what we call Stokes lines, okay? And on one side of the line, the function starts it starts decaying exponentially, and it's very polite. But on the other side of the line, if you cross the line, it suddenly wakes up, and the function starts oscillating extremely wildly, and this is called the Stokes phenomenon. So even though the function itself is smooth, there's an asymptotic behavior, as you can see, where essentially it's discontinuous. Okay, and by understanding these sectors here is really crucial for quantum mechanics and wave optics. Okay, so we also have other methods. Again, if you recall from our previous series, the derivative is just a linear map. Okay, and so partial differential equations, whatever, they're not really you usually solve them with linear equations. Okay, you usually factor them out or find some characteristic way to solve partial differential equations in terms of linear ODEs. So just study ODEs really a lot, and study complex analysis, and study functional analysis and all these things. Okay, special functions. Okay, because that's usually what you're doing to get ODEs. All right, but there is another way to solve partial differential equations, and we're going to discuss that here, which are integral transforms. Now, the Laplacian Fourier transforms, these allow us to diagonalize differential operators, and we'll go more on that in the next episode. But Green's functions is worth mentioning here, because we can solve an inhomogeneous equation here, some linear map on U to be equal to F, and express this as an integral kernel. So if we integrate the function with respect to G here, which represents the impulse response of the system, the physics of the operator will then solve the differential equation. So that's also worth mentioning. This is an exact way to solve differential equations. The asymptotic analysis, when we can't solve a problem exactly, we need to approximate it. And one of the most important tools in our arsenal is the WKB approximation. And this is typically used when the energy is high and we have rapidly oscillatory systems. Okay? Or the wavelength is just short, in other words, right? So that's essentially what this epsilon here is doing. All right. Now, what this allows us to do is describe a particular classic, well, if we expand really S here, the phase of that solution that we want to encode, what it gives us is the classical iconal equation, which is useful for describing rays of light or beams. And this solves partial different, or just solves ordinary differential equation. And the transport equation for the amplitude of the wave. Okay, so this typically, the solution for the WKB approximation being applied takes on the form here, and we can link essentially wave solutions to classical ray trajectories. All right, so this blue line here is the exact solution. And our WKB approximation, it's not rendering, but essentially it's a way to approximate it. And what it's going to do is blow up here, okay, at this turning point. So it solves this part, but there should be an orange line. It's just not rendering. But what it does is it blows up at the turning point, okay, and it just diverges. But what we can do is just notice really that the approximation is excellent on the left, but on the right, really we need a way to smooth this turning point here, where the rapid oscillation, starts to become more so part of the classical ray tracing. So we just need area functions, right, to look at the patch and to patch the two sides together. All right. Now, what we also can try to do is construct something called perturbation theory. And for nonlinear problems, we can choose to just expand out near a linear limit and just kind of make it nonlinear by expanding it in terms of some epsilon squared, etc. But if the problem is nonlinear, but just slightly nonlinear, we expand the solution to series, and we can think of like a Duffing oscillator, which is a pendulum, but instead a pendulum has a nonlinear spring. So usually pendulums themselves are have some secular terms, like some damping on that spring, or so in terms of the sign, the G sine theta, that's like allowing the pendulum to go on some phase space or whatever, and it grows unbounded in time, right? Well, what we can do is just perturb that solution, but the problem with perturbing the solution is we need to invoke the Poincare and Lindstedt method, which is by creating a time coordinate that's a little bit stretched out, so that we can match it with, or we can choose frequency corrections to kill resonant terms that cause it to blow up, right? Because it essentially is an artifact of the time coordinate that we're choosing, where there's essentially a resonance that happens, and if you just naively perturb the solution, it blows up, okay, to infinity. So but if we particularly find where epsilon gets from the perturbation, where it gets closer and closer and closer to the exact, it gets closer and closer and closer to the exact solution, it's off by a little bit of a phase. But if we take out that part, then we can take control of the amplification, or remove the amplification or the secular growth that's happening by just getting rid of or by introducing the strain time coordinate. Okay, so that's the Poincare-Lindstedt method. Finally, we're going to arrive at the dark secret of analysis. Okay, and this is what all of quantum electrodynamics relies on, which is the theory of renormalization and resummation. So most series expansions that we use in physics, or even fluid dynamics, actually don't converge. So expanding out a series, it's growing factorially. The coefficients are growing factorially, and they're getting bigger and bigger, And so if you look at a Euler series here, just a regular plain divergent series here, what happens is that if we first look at lower order terms, so if we just take the partial sum, right, we can see that it's like, we're adding it, and it kind of, it's behaving a little bit. And with the partial sums, if we add more terms, though, it doesn't just get bigger, it gets worse and worse and worse, and it starts swinging wildly to negative and positive infinity each time, right? But if you notice over here, it's actually kind of converging to a value, but the tail end is just doing its own thing, right? So it's kind of strange, right? Like, we have the infinity here, but like it's converging to something. And so this is why people are like, oh, you're sweeping infinities under the rug. But it's like, no, like just expand out the partial order, right, sum, and see, it doesn't matter how much that infinity blows up. Like, there's still something that there's a sum here that's converging, right? Even though the series itself diverges. This information here is really important for physics, because of course, again, the asymptotes or the divergences, or the holes in our solutions are not physical, right? We saw that earlier with the Riccati equation, or even with the Bernoulli equation in general. So because of the coordinate system that we chose. So what we need to do is do that in reverse. This is what the Borel summation is. And so we take the transform of the series to tame the factorials and sum it up, and then transform it back. And we'll get a horizontal line then, which that horizontal line is called the Borel sum, and that's what this is here. It extracts a finite physical number from a mathematical kind of explosion, okay? So that's the precursor to something called the renormalization group, which we'll talk about in later levels. But so far, we have gone from exact integration. Again, we've gone from the idea of exact integration, to artifacts of our perspective of our coordinate system, to chaos, and chaos then necessitated also special functions also have divergences, and the divergence necessitates ways of perturbing them slightly, or just completely doing renormalization to get the coherent sum that is the Borel sum that it's going to. So again, as we go further, we're going to need a new language to handle these infinities. What if we have infinite dimensions and rough geometry, right? And of course, those integrals are going to blow up, right? Or those infinite series are going to blow up. So that's essentially what we're going to cover, in this series. That's the whole goal. Here's the references that you can look at, and we're going to build essentially the cathedral of functional analysis next episode. All of these are going to be available on my website. You can also check the Discord for updates, but these notebooks are going to be available to everybody. So thank you for following along, and I'll see you guys next time.